Welcome to the deep dive. Our mission today is to really cut through the noise and deliver your competitive edge on a technological convergence. I mean, it's so vast. It's literally creating a new layer of planetary intelligence. We are diving deep into the fusion of artificial intelligence, the Internet of Things, 5G, 5G Advanced, and the incoming wave of 6G.
Yeah, we're not just talking small steps here, are we? This isn't just about incremental upgrades. We're really tracing how this whole tech stack, this, comprehensive combination, is transforming fundamental global infrastructure.
How so? What's the core change?
Well, it's moving it from static, isolated systems like, say, transit hubs or rigid power grids into what our sources keep calling living, learning organisms.
Living, learning organisms, that phrase. It's compelling, definitely. But it also sounds a little, I don't know, utopian, maybe a bit sci-fi. What does learning actually look like when it's built into infrastructure? Is there a risk of, autonomous failure? Or does it really mean we're moving beyond just reacting?
Reacting to problems like traffic jams or system failures.
Exactly. Are we moving to predicting and preventing them autonomously? But crucially, with genuine safety checks built in.
Right. Ideally, it's the second one. The learning element, it refers to AI models constantly optimizing. They're predicting based on this nonstop flow of real-time data. This allows the infrastructure to self-regulate, maybe even self-heal in some cases. It's really about building in resilience.
Okay, resilience and prediction rather than just reaction.
Precisely. And the scale of this change, it's not some far-off future thing. It's already immediate in certain high-stakes environments. Take aviation, for instance, as a perfect example.
Aviation. How's it playing out there?
Well, look at the market figures. The global 5G and aviation market. It's projected to absolutely skyrocket. We're talking from maybe $1.2 billion in 2023 to a staggering $50 billion by 2033.
50 billion. Wow, that's a compound annual growth rate of 45.4%. That isn't just growth. That's, like you said, an explosion. It has to be fueled by necessity.
Yeah, it absolutely is.
If that kind of money is pouring in, they must be solving some really crucial, really immediate problems. And that brings us right into our first focus area, how AI and 5G are redefining the airport experience, like right now.
The AI plus 5G airport is, I think, the perfect starting point to really get our heads around this revolution. Because it's a controlled environment, but it's incredibly high stakes, a microcosm of the whole thing.
Makes sense. A complex system in a box, almost.
Exactly. At its core, it's a data-driven ecosystem. If you think about an airport as this incredibly complex, high-speed machine, AI is essentially the operational brain. It handles the analytics, the prediction, the automation.
Okay, AI is the brain.
And 5G provides the nervous system, the ultra-fast, ultra-reliable digital nervous system connecting absolutely everything in real time.
And when you say ultra-fast, we are talking about 5G or even 5G advanced, right? Promising peak speeds, what, up to 10 gigabits per second?
Up to 10 GBPs, yeah.
Yeah.
And critically, latency the delay down as low as 1 millisecond.
1 millisecond. That near-instant communication is just essential for systems where even a tiny delay, maybe a second or two, could be catastrophic.
Absolutely. Think about ground vehicle control or security alerts. But the crucial components here, they aren't just the public Wi-Fi you could connect your phone to.
Right, it's deeper infrastructure.
Much deeper. The real transformation hinges on private 5G or P5G networks. This is key. P5G provides the airport with its own dedicated, secure, licensed slice of bandwidth.
Licensed, so they actually own a piece of the spectrum.
Or lease it long-term, yeah. Sometimes specific bands are set aside for enterprise use, and this is absolutely vital for mission-critical operations. Coordinating air traffic control instructions, secure communication between ground vehicles, automated security systems, baggage handling, all the nuts and bolts.
So P5G is like airport having its own exclusive high-speed railroad track just for its internal operational data, completely separate from the public internet traffic.
That's a great analogy. Totally separate, totally secure, and optimized for low latency and reliability.
But if P5G is private, who actually owns that spectrum? Is it the airport authority? A mobile operator? A systems integrator? And maybe more importantly, how does the airport, monetize that capacity? Or just ensure it works smoothly with the dozens of different airlines operating on site? That interoperability must be a nightmare.
That's definitely where the complexity lies. Often, it's the airport authority itself, or sometimes a dedicated systems integrator they partner with that owns and manages the P5G spectrum and network.
Yeah.
As for monetization, it's less about selling bandwidth directly to airlines, though that might happen for certain services. It's more about the massive improvements in overall efficiency.
So the return is indirect.
Mostly, yes. offering airlines reduced turnaround times, fewer delays, smoother baggage handling. These are huge cost centers for airlines. If the airport's infrastructure makes their operations cheaper and more reliable, that's the value proposition. It becomes a competitive advantage for the airport itself.
Okay, that makes sense. The value is in the improved operational performance it enables.
Exactly. And that P5G infrastructure, that private track, it has to work hand in hand with another critical piece, mobile edge computing, or MEC.
Right, MEC, I've heard that term a lot. How does it fit in here?
Precisely. This synergy is crucial. Think about it. Instead of sending really time-sensitive data like, say, a critical baggage tag scan that needs an instant routing decision, or maybe a ground collision avoidance warning from a sensor on a tug.
Instead of sending that all the way back to some distant centralized cloud server hundreds, maybe thousands of miles away.
Right, which introduces latency just from the travel time. MEC processes that data locally, right there at the edge of the network, often on servers located physically within the airport grounds.
So P5G gives you the reliable track, the dedicated connection.
And MEC gives you the local processing power, like having a mini data center right there making decisions instantly. This enables those critical real-time control loops, absolutely necessary for things like autonomous ground vehicles needing to react in milliseconds or for immediate security threat detection and response.
Got it. Private network for reliability, edge computing for speed. Let's dig a bit deeper into the specific capabilities being built into this whole technology stack. Beyond just the raw speed of 5G, what's 5G Advanced or 5GA bringing to the table that's new?
Okay, 5G Advanced, 5GA. This is the immediate evolution, the next step that's rolling out now. The really breakthrough feature here, the one people are excited about, is integrated sensing and communication, often called ISAC.
Integrated sensing. So it senses and communicates.
At the same time, using the same hardware and radio waves. This isn't about just adding separate radar systems all over the airport, though those exist too. It's about leveraging the existing massive MIMO antenna arrays.
Those complex multi-element antennas already used for sending and receiving lots of data streams in 5G.
Exactly. Leveraging those arrays to simultaneously function as a kind of high-resolution radar.
Wow. So the network equipment itself, the base stations, they become sensory organs, not just communication devices.
That's precisely the idea. It gives the airport this radar-like environmental awareness, but it's woven directly into the communication system fabric. It's incredibly efficient.
What can it actually do? What kind of sensing?
It allows the airport to detect and track things, everything from unauthorized micro-drones flying near restricted airspace, or even large birds near the flight path, which are a serious hazard.
Right, bird strikes.
To providing hyper-precise positioning for vehicles moving around on the tarmac, even in really bad weather conditions like fog or heavy rain, where cameras struggle. It can map the radio environment, detect interference. It's a whole new layer of situational awareness baked into the network.
That feels like a fundamental shift in safety capability. Okay, so you have this robust sensing from 5GA, the reliable connectivity from P5G, the fast processing from MEC, and then you layer the AI on top of all that. What specific AI components are doing the heavy lifting here?
Our sources generally point to three primary functional areas where AI is making the biggest impact. First, you've got machine learning. This is constantly analyzing historical and real-time data to predict operational demands and optimize the flow of everything: planes, passengers, baggage, ground crew.
So it's not just predicting, say, if a flight might be delayed.
No, it's much more granular. It's forecasting minute-by-minute crowd behavior inside the terminals, predicting where queues are likely to form at security or check-in before they happen. It's anticipating bottlenecks and dynamically allocating resources, staff, gates, ground equipment proactively before a crisis even develops.
So it's not waiting for the security line to snake around the corner. It's seeing the passenger flow data, predicting the peak 15 minutes out, and automatically signaling to open more security channels or deploy more staff there.
That's absolutely the goal. Proactive, predictive resource management. Second main area, computer vision. This is powering a lot of the core security and logistics functions we're seeing.
Like facial recognition.
Yes, that's a big one. Biometric identification, using facial recognition for seamless, contactless passenger processing check-in, bag drop, boarding. But it's also used for automated baggage tracking, reading tags accurately at high speed, even monitoring baggage condition, and of course, security surveillance detecting anomalies, unattended bags, restricted zone breaches.
Okay, machine learning for prediction, computer vision for seeing and identifying. What's the third?
Third is predictive analytics. This takes a slightly longer view, often integrating data from multiple sources. It's forecasting resource demands further out, optimizing fuel distribution schedules, strategically assigning gates to minimize aircraft taxi time and fuel burn. And a huge one is predictive maintenance for aircraft and ground equipment, analyzing sensor data to predict when a component is likely to fail rather than relying on fixed maintenance schedules.
Right, fix it before it breaks and causes a delay.
Exactly. And the output of all this AI analysis, this constant learning and prediction, feeds into creating this increasingly autonomous airport environment, which relies on supporting infrastructure like digital twins.
Ah, the digital twin concept. Explain that a bit more in the airport context.
A digital twin is essentially a highly detailed, dynamic, virtual replica of the entire airport. The physical infrastructure, the systems, the processes, even the real-time flow of people and planes. It's constantly updated with data from the real airport.
What's it used for?
Multiple things. Simulation is key. You can test changes like a new boarding procedure or altering taxiway usage in the virtual world first to see the impact without disrupting actual operations. You can run what-if scenarios for emergencies. It's also used for training staff in a realistic virtual environment.
And you also mentioned AR/VR interfaces.
Yes, augmented reality, AR, and virtual reality, VR, are becoming important interfaces. Think about a maintenance technician working on a complex piece of equipment in a hangar. They could wear AR glasses that overlay instructions, diagrams, or sensor readings directly onto their view of the machinery. Or an expert located remotely could see what the technician sees and provide real-time guidance through that interface. VR is used more for immersive training simulations.
Okay, the combination of P5G, MEC, 5GA sensing, multiple AI layers, digital twins, AR/VR, it's a formidable tech stack. Now let's talk hard returns. Where's the real ROI, the payback, on what must be a massive investment?
Operational efficiency has to be the biggest driver, no question.
Makes sense. Time is money, especially in aviation.
It absolutely is. The integration of AI plus 5G is projected by several analysts to cut flight delays globally by up to 20%. That is a huge number.
20% fewer delays. How is that actually achieved?
It's a combination of factors. Better gate and runway scheduling, as we discussed. Predictive maintenance is a major contributor. Sources suggest it can reduce aircraft downtime by as much as 40%. When an aircraft isn't available, that cascades into delays. And then there's the automation of ground handling tasks. Things like precision refueling, automated baggage loading, autonomous towing vehicles moving aircraft. Automating these frees up human resources and, crucially, shaves off critical minutes from turnaround times.
20% fewer delays. That translates directly into billions in saved operational costs for airlines' fuel, crew time, passenger compensation. And, of course, massive increases in passenger satisfaction.
Exactly. It's a win-win. Then there's security enhancement.
How does this stack improve security beyond just more cameras?
Enhanced security leverages that high-speed, low-latency P5G MSC infrastructure. You can deploy many more high-definition 5G-connected cameras, streaming rich video data. AI analytics constantly monitor these feeds, detecting anomalies far faster than human operators could. Unattended bags, unusual loitering, unauthorized personnel entering restricted areas, even subtle changes in crowd flow that might indicate a problem.
Within seconds, you said.
Literally within seconds for many types of alerts. And the 5GA integrated sensing adds another layer. Constant, precise runway monitoring, detecting foreign object debris, FOD, which can be incredibly dangerous. Ensuring safe operations even in very low visibility conditions where pilots can't see the runway clearly.
Okay, efficiency and safety are clear benefits. What about the push towards sustainability? How does this tech stack play into those crucial green goals?
Sustainability is now being structurally engineered into the airport's operations using this tech. It's not just an afterthought. AI models dynamically optimize energy consumption across the entire campus.
How? Where are the savings?
Think about lighting dimming lights in unused areas, heating, ventilation, and air conditioning, HVAC, adjusting based on real-time occupancy and weather forecasts. Managing the charging schedules for growing fleets of electric ground support vehicles to minimize peak load on the grid. By using real-time data and predictive AI to manage these massive power loads intelligently, airports are projected to reduce their overall carbon footprint by up to 30%. This aligns directly with the ambitious net zero targets many major hubs are publicly committing to.
30% reduction is substantial.
Yeah.
Okay, so the airport runs better, safer, greener. What about the passenger? If the airport is busy running itself efficiently, is the experience actually, fundamentally better for us travelers?
The goal, increasingly, is the invisible airport experience. Seamless, frictionless. We're seeing personalized, contactless travel becoming the norm, facial recognition check-ins, automated bag drops where you barely interact with anyone, e-gates using biometrics for security and boarding.
Do those actually speed things up?
Studies consistently show they do. Biometric and e-gate systems can lead to 50% faster security screening and boarding processes compared to traditional manual checks. Less queuing, less hassle. Plus, AI-enabled airport apps are becoming more sophisticated, using AR wayfinding inside the terminal to guide you directly to your gate, providing real-time updates on flight status, even pre-ordering food via the app. It's all aimed at reducing passenger stress and terminal congestion.
So this isn't just theoretical stuff planned for the future. It's being deployed right now, you're saying. Which specific global cities or airports are really pushing the boundaries on this technology stack already? Where can we see it in action?
Yeah, definitely not just theory. We can point to several global pioneers already implementing significant parts of this. You mentioned Incheon International Airport in South Korea. They were an early adopter, using AI and MEC since around 2020.
What were they focusing on?
Their initial focus was heavily on real-time security screening enhancement, using AI to assist human screeners, but also things like robotic cleaning and hygiene maintenance, especially post-COVID, and predictive equipment checks for things like baggage systems. They really tackled efficiency and safety in tandem from the start.
And Beijing Daxing International Airport, the huge starfish-shaped one, it was built with 5G connectivity integrated from day one, wasn't it?
It was. Daxing really pioneered the large-scale use of biometric boarding face scanning to board the plane and deployed robotic baggage handling systems right when it opened. It clearly showcased that AI-first terminal design philosophy, a statement piece.
But you mentioned an even more advanced application using that 5G sensing technology.
Right. For the really cutting-edge stuff, leveraging that integrated sensing capability we talked about, look at Baoshan Yunrui Airport in China.
Baoshan Yunrui. Tell us more about that one. What makes it stand out?
Baoshan Yunrui is being specifically developed and designated as the world's first fully 5G smart airport. This is where that integrated sensing concept really comes to life in a practical application. They use those 5G base stations, equipped with sensing capabilities, deployed across the airport perimeter and along the runways, their primary use case, to actively track and identify small, non-cooperative objects.
Non-cooperative meaning?
Meaning things that don't have transponders, like birds or unauthorized drones. The system can detect them, classify them, and track their movement in real time, providing immediate, precise data to air traffic controllers for safety interventions, preventing bird strikes, detecting drone incursions.
That's a critical safety function, directly using the network's perception capability. It's a showcase of the leap from just providing connectivity to providing active environmental awareness.
Exactly. It demonstrates the potential of 5G beyond just faster data speeds.
It really sounds like the airport is evolving, doesn't it? From just a place planes take off and land into a key economic and strategic node. It's collecting vast amounts of mobility data, operational data, data that could potentially inform urban planning, traffic management, even emergency response for the entire surrounding region.
It absolutely is becoming a miniature smart city in its own right, a highly optimized, increasingly self-managing hub of activity and data.
Okay.
And this transition, seeing the airport as a 5G-powered microcity almost, sets the stage perfectly for thinking about the next generation of connectivity, 6G. How do we scale this intelligence up?
Okay, so we've established how 5G, 5GA, and AI are creating this optimized, almost self-regulating digital nervous system for the complex environment of an airport, a microcity, as you put it. But what happens when you try to scale that kind of cognitive approach, that intelligence, across an entire sprawling megalopolis?
Yeah.
And then maybe even beyond that, globally. What's the fundamental leap from 5G to 6G? Is it just faster speeds again?
Speed is part of it, yes, but it's not the main story. The truly fundamental shift, the leap, is from 5G enabling high-speed connectivity for applications to 6G having native intelligence.
And native intelligence, what does that mean in practice?
It means 6G is being designed from the ground up to be AI native. Intelligence isn't just an application running on top of the network. AI and machine learning principles are woven into the fabric of the network itself, at every level.
So the network itself thinks?
In a way, yes. It enables truly predictive autonomous orchestration. The network can manage its own resources dynamically, it can potentially heal itself by rerouting traffic around faults, and crucially, it can anticipate user needs, whether that's bandwidth, latency, or specific services before they even fully materialize. It's proactive by design.
Okay, AI baked into the network core. What about the performance metrics? We thought 5G was fast. What are we even aiming for with 6G?
We're moving into performance figures that sound frankly, almost astronomical compared to today. 6G is targeting peak speeds of up to 1 terabit per second, TBPS.
1 terabit, that's 1,000 gigabits per second, so roughly 100 times faster than the theoretical peak of 5G.
Potentially, yes. At least 100 times faster than the current typical 5G standard. And latency, the delay is expected to drop even further into the sub-millisecond range, microseconds, potentially.
How is that even possible? What technology enables that kind of leap?
Primarily, it involves moving up to much, much higher frequencies. 6G will utilize terahertz frequencies, sometimes called sub-millimeter waves. These bands offer enormous chunks of bandwidth, which is what allows for those incredible speeds.
Terahertz. That sounds challenging. Don't those super high frequencies have trouble penetrating obstacles or traveling long distances?
They absolutely do. That's one of the core technical hurdles for 6G. Terahertz signals are easily blocked by walls, objects, even rain or atmospheric gases. Their range is much shorter than current cellular signals. Overcoming this requires fundamentally new approaches to network design.
Okay, so massive speed and near zero latency, but significant challenges with range and penetration. It sounds like 6G needs more than just faster chips. It needs a whole new architecture.
Exactly. 1 TBP speed is almost irrelevant if the signal can't reach your device reliably. So, beyond raw speed, the real differentiators for 6G are architectural resilience and achieving truly ubiquitous three-dimensional coverage. And that hinges on a concept called SAGIN.
SAGIN, what does that stand for?
SAGIN stands for Space Air Ground Integrated Networks, and it's seen as the absolutely necessary backbone for 6G, especially for applications like aviation, global logistics, autonomous vehicles, and connecting remote areas.
Space air ground, so integrating satellites.
Yes, but much more than just satellites. It aims to create a seamless, continuous, highly resilient three-dimensional network fabric. This means tightly integrating traditional ground-based terrestrial systems, the cell towers, with multiple non-terrestrial layers.
What kind of layers?
We're talking constellations of low Earth orbit, LEO satellites, like Starlink or OneWeb, providing global coverage. But also high-altitude platforms, HAPs.
HAPs, like drones or balloons.
Exactly. Think semi-permanent solar-powered drones or specialized balloons operating way up in the stratosphere, maybe 20 kilometers high. They can loiter over a specific area for months, acting like floating cell towers, providing coverage to a large region below. And potentially swarms of lower-altitude traditional UAVs, drones, acting as temporary mobile relays or hotspots.
So it's a multi-layered cake of connectivity. Ground, drones, HAPs, LE satellites, all working together.
Precisely. The idea is seamless handover between these layers. So if a severe storm or maybe a natural disaster like an earthquake takes out a ground tower in a critical area,
the LEO satellites and maybe a nearby HAP could automatically pick up the slack, providing resilient, multi-layered coverage without any noticeable gap in service for users on the ground or planes in the air.
that's the vision. Total resilience through redundancy and integration across domains. But imagine the technical complexity, the handoff protocols required to transition a data stream seamlessly between, say, an aircraft receiving data from a LEO satellite that's whizzing overhead at 17,000 miles per hour.
Passing that connection maybe to an HAP miles above the clouds, and then down to a terrestrial 6G tower as the plane descends, all without dropping the connection or introducing lag.
Exactly. SAGIN needs to manage that incredibly complex real-time synchronization and orchestration across vastly different platforms, moving at different speeds and altitudes. It's a huge challenge, requiring significant AI for network management.
That complexity must be even greater inside buildings, like our airport example. All that dense concrete steel structures, underground levels, creating lots of signal dead zones, even for current networks. Terahertz signals would struggle even more there, wouldn't they?
Absolutely. Indoor penetration and coverage in complex environments is a massive challenge for Terahertz. Which brings us to another key enabling technology pillar for 6G, reconfigurable intelligent surfaces, or RIS.
RIS, reconfigurable intelligent surfaces. What are those?
Think of them as smart, electronically controllable surfaces or panels. They might be integrated into walls, ceilings, windows, maybe even painted onto surfaces eventually. They are passive, meaning they don't transmit their own signal, but they can intelligently manipulate incoming electromagnetic waves.
Manipulate how?
They are made up of many small, individually controllable elements, often using metamaterials. By adjusting the properties of these elements, like their phase shift, the RIS can essentially reflect, redirect, scatter, absorb, or even focus radio waves in a software-defined way.
So they act like smart mirrors for radio waves, actively steering the signal around obstacles or concentrating it towards a user.
That's a very good way to think about it. They can effectively eliminate dead zones within complex structures like airport terminals, factories, or dense office buildings. They can improve signal strength, reduce interference, and even enhance security by directing signals precisely where they need to go and not elsewhere.
That's fascinating, almost like tuning the physical environment itself to optimize wireless communication. But how do these surfaces know how to configure themselves? How do they know the optimal way to reflect or steer the waves?
That's where the AI native aspect of 6G comes right back in. The RAS panels don't operate in isolation. They need to be controlled intelligently, often in coordination with the base stations. This is where techniques like edge federated learning, EFL, and deep reinforcement learning, DRL, become crucial.
Okay, EFL and DRL. Can you break those down simply?
Sure, deep reinforcement learning, DRL, is a type of AI where the system learns through trial and error. In this context, the AI controlling the RIS, or a network segment, would try different configurations, adjusting the phase shifts on the RIS elements, maybe changing beam-forming patterns from the base station. It then observes the result. Did the signal quality improve? Did energy consumption go down?
And it gets a reward or penalty based on the outcome.
Exactly. Based on that feedback, it learns over time which configurations work best in the current, constantly changing radio environment. It's constantly experimenting and optimizing.
And federated learning, EFL.
Edge federated learning, EFL, is important for privacy and efficiency. Instead of sending all the raw training data from the edge devices, like user phones or RAS controllers, back to a central cloud AI, the learning happens locally at the edge. Only the learned model updates, not the raw data, are shared and aggregated. This keeps sensitive user data private and reduces the communication overhead.
So the network is essentially running millions of tiny distributed experiments across all its components, base stations, RIS panels, even user devices, constantly testing configurations, learning locally, and sharing insights to find the most efficient and reliable path for data, all while protecting the information itself.
That's a great summary. It allows the network components, the RAS, the base stations, to self-optimize connectivity and potentially enhance security simultaneously, adapting in real time to the dynamic environment without always relying on explicit commands from a central controller. The computational demands are immense, but it's seen as necessary for the kind of hyper-reliability and performance 6G is promising.
Okay, AI native network, SAGIN for coverage, RAS for propagation, EFL DRL for optimization. Let's fast forward conceptually to the 2030s when 6G might be commercially deployed. What are the truly game-changing 6G use cases we're likely to see specifically in aviation, building on the 5G foundation?
Well, first, expect a really radical step up in enhanced air traffic management, ATM.
Right.
That SAGIN architecture we talked about, linking aircraft, ground systems, satellites, HAPs, allows for hyper-real-time, globally consistent route optimization and trajectory management.
More precise than today's systems.
Much more. Think 4D trajectory management, latitude, longitude, altitude, and time synchronized globally. Sources suggest this level of integration and predictive capability could cut operational delays caused by air traffic congestion and inefficiencies by potentially up to 25% compared to current levels.
A quarter of global air traffic delays just wiped out through hyper-optimized, satellite-integrated, AI-driven logistics. That is, again, a massive economic impact, not to mention fuel savings and emissions reduction.
Huge impact. And this kind of ultra-reliable, low-latency, high-bandwidth 3D network is absolutely essential infrastructure for future transportation modes we keep hearing about.
You mean things like flying taxis?
Yes, exactly. Urban air mobility, UAM. Autonomous air taxis, carrying passengers across cities, large-scale drone logistics, delivering packages. This entire vision relies completely on 6G level connectivity. You need robust, secure 3D communication and coordination capabilities to manage potentially thousands of autonomous aircraft operating safely in congested urban air corridors. That requires ultra-reliability, guaranteed sub-millisecond latency for automated collision avoidance systems, and precise positioning, all things 6G aims to deliver via SAGIN and other technologies.
It really unlocks that third dimension for urban transport. And on the security side, within the airport environment, what comes after the facial recognition we see now?
We likely move into more sophisticated advanced biometrics, not just recognizing a face, but potentially combining face recognition with gait recognition, how a person walks. This, combined with AI analyzing behavior patterns within those digital twins of high security areas, could provide continuous passive monitoring and much more granular access control, identifying suspicious behavior patterns, not just unauthorized faces.
That sounds intense. And what about inside the aircraft itself? How does 6G change things there?
6G enables what's being called aeronautical edge computing, AEC. This means much more powerful computing and AI processing happening on the aircraft, but tightly synchronized in real-time data loops with ground control towers, maintenance centers, and even nearby ground vehicles via the 6G network.
What kind of data loops are we talking about?
Continuous high-bandwidth streams of aircraft health monitoring data sensor readings from engines, control surfaces, avionics being analyzed both on board and on the ground simultaneously. Immediate transmission of critical threat updates like severe weather detected by ground radar or another aircraft. Synchronized operational data for optimizing landings, taxiing, and gate connection. It essentially makes the aircraft itself a highly responsive, intelligent node within the broader cognitive aviation network.
Okay, this technology isn't just theoretical diagrams. You're saying global research is actively defining the standards and building prototypes right now. Where are we seeing this emerge?
Absolutely. Standards bodies like the ITU are deep in the process. And yes, prototypes are being built. For example, the UK's ARIS project is a 6G research initiative specifically focused on using RIS technology in aerospace environments.
What are they finding?
They're using those RIS panels combined with the EFL DRL optimization techniques we discussed to improve connectivity within challenging spaces, like aircraft hangars and maintenance bays environments full of metal that wreak havoc on radio signals. Early simulations and lab tests are showing potentially a 40% improvement in signal stability, coverage, and even physical layer security using RIS compared to traditional systems.
A 40% improvement is significant in those tough environments. And it seems for rapidly expanding economies, investing in 6G isn't a luxury. It's being treated as a strategic necessity for future growth.
Indeed. Look at India's National Bharat 6G vision. It's a major government initiative. A key component of their plan is integrating advanced concepts like aeronautical edge computing, AEC, into the design of 42 new airports they're planning or currently building.
42 airports being designed with 6G era concepts in mind.
Yes. This massive infrastructure investment is seen as critical because air passenger traffic in India is projected to nearly double in the coming years, jumping from around 220 million annually now to potentially 425 million. They recognize they need this massive leap in network scalability, intelligence, and safety capacity to handle that kind of explosive growth efficiently and safely.
So the overall vision, maybe looking out to 2035 or so, is that airports will no longer be just these isolated transit hubs. They become truly integral, active parts of the surrounding smart urban environment.
That's absolutely the trajectory. They evolve into cognitive hubs, operating with significant autonomy, seamlessly integrating ground and air traffic, hosting corridors for urban air mobility vehicles, maybe even serving as secure nodes for future quantum communication networks, handling sensitive defense or financial data transfer. The future airport aims to be self-managing, anticipating problems before they happen, constantly learning and evolving in sync with the city around it. It positions itself not just as a transport link, but as a core nerve center of the smart metropolis.
Okay, so we've seen the airport as a kind of controlled testbed evolving into a cognitive hub. Now, let's scale up. Moving from that relatively controlled airport environment to the sheer scale and, frankly, chaos of a modern megalopolis. The challenges facing smart cities seem absolutely monumental. We're dealing with this massive demographic shift towards urban living that seems to make predictive, intelligent infrastructure mandatory, not just a nice to have.
That really is the crux of it, isn't it?
Yeah.
The numbers are stark. By 2050, the UN projects nearly 70% of humanity, that's over 6.5 billion people, will be living in open areas. You simply cannot manage that density, that complexity, with purely reactive governance anymore. Fixing potholes after they form, managing traffic jams after they gridlock. It doesn't scale.
So the shift is towards predictive intelligence.
Entirely. Predicting infrastructure decay before it fails, managing traffic flow proactively, optimizing energy distribution in real time. It's about moving from reacting to crises to actively preventing them through data and AI.
And the economic forecasts seem to back this up completely. The global market for AI, specifically in smart city applications, it's valued around $50-odd billion in 2025, but it's projected to soar to over $460 billion by 2034. That's nearly tenfold growth in under a decade. That explosive growth shows the sheer urgency cities feel about implementing these solutions.
It does. And the 6G smart city technology stack is being designed specifically to handle this kind of hyperscale complexity and density. We talked about 6G speeds, but maybe even more important for cities is its ability to handle connection density. 6G aims to enable the Internet of Everything, IoE.
IoE, not just IoT.
Right, connecting potentially up to 10 million devices per square kilometer. Think about the sheer volume that implies. Every smart traffic light, every environmental sensor measuring air quality or noise levels, every smart parking meter, every connected water meter, every autonomous delivery bot, every public transport vehicle, maybe even sensors embedded in roads and buildings,
Mm.
all connected endpoints generating data.
10 million devices per square kilometer. That density is just staggering. What are the technical challenges involved in just managing that many connections simultaneously? Without massive signal interference, draining batteries on all those tiny sensors, creating huge data bottlenecks.
Oh, the challenges are enormous. It requires incredibly sophisticated radio resource management techniques, things like ultra-dense cell deployments, picocells, femtocells, advanced beamforming to focus signals precisely, dynamic spectrum sharing, and extremely efficient power management protocols, especially for low-power IoT devices that need to last years on a single battery.
And this is where some of those advanced 6G features come in again, like integrated sensing.
Exactly. Integrated sensing and communication, ISAC, becomes even more critical in the dense urban environment. Why deploy separate sensor networks for everything if the communication network itself can sense? Radio waves used for 6G communication can simultaneously be used to sense the environment,
What kind of sensing?
tracking pedestrian flows in public spaces to manage crowds, monitoring traffic density and vehicle speeds without needing extra cameras, detecting pollution levels, or even gas leaks by analyzing signal propagation changes. Maybe even monitoring the structural health of bridges or buildings by detecting minute vibrations through radio analysis. It offers a way to gather rich environmental data much more efficiently and pervasively.
Okay, so ISAC helps gather the data, but managing all that data and securing the critical systems it controls requires even more advanced infrastructure components, doesn't it?
Absolutely. For security, especially protecting critical national infrastructure like power grids, water systems, emergency services, communication, and financial hubs, quantum communication technologies are being seriously considered as part of the 6G roadmap.
Why quantum?
Because of the threat from future quantum computers, which are expected to be able to break today's standard encryption algorithms, like RSA, relatively easily, quantum communication techniques like quantum key distribution, QKD, offer theoretically unbreakable encryption based on the laws of physics, protecting those vital data streams against future attacks.
So future-proofing security, what about managing transactions and data integrity?
That's where technologies like blockchain come into play. Beyond cryptocurrencies, blockchain offers a secure, transparent, and immutable ledger. In a smart city, this could be used for things like secure peer-to-peer energy trading, where homes with solar panels can automatically sell excess energy back to the grid or directly to neighbors with transactions securely recorded.
Yeah.
It could also provide transparent and auditable data trails for municipal services, tracking resource usage, or even enabling secure digital identity systems for citizens.
Okay, quantum for security, blockchain for trust and transactions. How did the city actually manage and plan for this colossal influx of data and devices? How do they make sense of it all in a cohesive way?
The primary tool for that is becoming the digital twin. We mentioned it for airports, but for cities, it's even more critical and more complex. These are highly detailed, dynamic virtual replicas of the entire city, not just the physical buildings and infrastructure, but also the energy networks, the transportation systems, the water systems, environmental conditions, all continuously fed by that deluge of real-time data from the IoE sensors and systems.
And what's new here with AI?
These digital twins are increasingly being powered by advanced generative AI. This allows urban planners and operators to go beyond just simulating physics. They can now model and predict much more complex, often unpredictable human behavior within the city. How crowds might react in an emergency, how changes to public transport might affect commuter choices, the potential impact of new developments on traffic patterns.
So you can test policies or infrastructure changes virtually first.
Exactly. Use the digital twin to simulate everything from disaster scenarios like modeling flood inundation based on predicted rainfall, or simulating the cascading effects of a major power blackout to optimizing everyday operations, predicting the optimal placement for new electric vehicle charging stations, figuring out the best route for a new bus line, or assessing the environmental impact of a proposed construction project. It's a powerful sandbox for urban planning and management.
Let's dive into some practical AI applications that are actually making a difference in cities today or very soon. Starting with transportation, usually the biggest headache in any major city.
Transportation is being fundamentally restructured by AI and IoT. We're seeing widespread deployment of AI-powered adaptive traffic lights. These aren't on fixed timers anymore. They use cameras and sensors to analyze traffic flow and real-time vehicle counts, queue lengths, pedestrian presence, and AI algorithms automatically adjust the signal timings dynamically.
Adjusting across a whole network of signals.
Yes, optimizing flow across entire corridors or districts, not just isolated intersections. The impact is significant. Studies in cities implementing these systems show reductions in average travel times by up to 25%, sometimes even more during peak hours. The city's road network reacts instantly to changing congestion patterns.
Can you give us a concrete example of where this is working well?
Singapore's smart traffic system is often cited as a leader. They use deep machine learning models, fed by vast amounts of sensor and camera data, to predict traffic flow patterns up to an hour in advance and proactively optimize traffic light cycles across the entire island. The results are quantifiable. Millions of saved commuter hours annually, significant reductions in fuel consumption because cars spend less time idling, and lower vehicle emissions. It's a clear win. Also think about things like advanced tolling systems, perhaps powered by companies like AMD, enabling free-flow highway tolling. High-speed cameras and AI identify vehicles without them needing to stop or slow down, seamlessly integrating payment and vehicle movement data into the city's broader mobility intelligence layer.
Okay, so transportation is getting smarter, more fluid. If transportation is the city's circulation system, then energy is its lifeblood. How is AI tackling the massive challenge and push towards sustainability in urban energy grids?
Sustainability is absolutely core to the modern smart city vision, and AI is critical here. We're seeing AI-enhanced smart grids being deployed. These grids use AI to analyze historical and real-time energy consumption patterns across the city, precisely forecast demand spikes, like during a heat wave, and dynamically balance the grid load.
Especially important with renewables, right? Solar and wind are intermittent.
Exactly. AI is crucial for integrating unpredictable renewable energy sources smoothly. It can predict solar generation based on weather forecasts, manage battery storage systems effectively, and even incentivize demand response, encouraging large consumers to reduce usage during peak periods. The impact can be dramatic. Look at data centers. Google famously used its DeepMind AI models to optimize cooling systems in their data centers and reduced energy consumption for cooling by 40%. Cities are now applying similar AI optimization principles to their much larger, more complex urban power systems.
40% is huge. Any city's leading the way on applying this citywide.
Copenhagen is a notable example. They have a very ambitious goal to be carbon neutral by 2025. A big part of their strategy involves using AI to optimize their district heating network, manage building energy consumption more efficiently, and integrate renewables into the grid. AI-driven optimization is seen as essential to actually hitting that near-term target.
An incredibly ambitious goal, really driven by AI's ability to manage complexity. Okay, what about public safety? How is AI enhancing security and emergency response in cities?
AI essentially acts as a tireless digital guardian for the city. The most common application is AI-powered video analytics. Cities have thousands of CCTV cameras. Humans can't possibly monitor them all effectively. AI algorithms can.
What can they detect?
They can be trained to detect anomalies, crowd surges, vehicles driving the wrong way, intrusions into restricted areas, abandoned objects, even the sound of gunshots or explosions via connected microphones. They can trigger alerts instantly, often pinpointing the location on a map. Cities using these tools consistently report significantly faster emergency response times, reductions of up to 80% in some cases, because first responders get accurate information immediately about what is happening and where.
Any examples here?
Amsterdam has implemented a sophisticated safety monitoring system that combines video analytics with data from environmental sensors and even social media sentiment analysis, trying to preemptively identify potential trouble spots or incidents. In natural disaster response, AI is also proving invaluable. Drones equipped with AI image processing capabilities are being used extensively in places like California to map wildfire boundaries in real time, assess damage after earthquakes or floods, and help guide rescue and resource deployment efforts much more effectively.
Finally, underpinning all these AI applications is the physical hardware layer, those millions of sensors, the ubiquitous IoT devices that form the city's digital nervous system, as the outline calls it.
Yes, the IoT layer is foundational. It's often silent, invisible, but crucial. It enables seemingly simple yet transformative systems that feed data to the AI. Take smart waste bins, bins with embedded sensors that signal municipal services only when they're actually full. This allows sanitation departments to optimize collection routes dynamically, skipping empty bins.
And that saves money.
Big time. Barcelona, for example, implemented this and reported cutting fuel costs and related emissions from their garbage truck fleet by around 40%. Fewer wasted trips, less fuel burned, less traffic congestion from slow-moving trucks. Another classic example is smart lighting. Streetlights equipped with sensors that dim automatically when no pedestrian or vehicle movement is detected, then brighten instantly when needed. The energy savings are massive, often providing a compelling return on investment, ROI, within just 2 or 3 years. IoT is essentially gathering the granular, real-time ground truth that AI then uses to reason, predict, and ultimately help self-manage the city more efficiently and sustainably.
The level of integration is really quite stunning when you lay it all out. We can clearly see how AI, IoT, and eventually 6G are being designed to make cities hyper-efficient, hyper-aware, hyper-intelligent. But I have to ask, this entire vision seems heavily focused on high-density, high-investment urban areas. What about the vast swaths of the world, the majority of the landmass that aren't hyperdense metropolitan zones? What about rural areas? That brings us to the really critical application of these technologies in connecting the traditionally unconnected.
That's right. And this is perhaps arguably the most socially significant application domain for this whole technology stack we're discussing. It's about leveraging IoT and AI to bridge that persistent, stubborn digital and economic divide between the connected city and the often underserved countryside.
What's the fundamental challenge here? Why haven't these areas been connected effectively before?
The core challenge in rural development is that you have to fundamentally redesign IoT and connectivity solutions for environments with often unreliable or non-existent traditional infrastructure. We're talking about places with maybe irregular or no electricity supply, very poor or patchy traditional cell phone coverage, and vast distances. You can't just copy-paste urban solutions.
So the tech needs to be more resilient, lower power, maybe longer range.
Exactly. Low power is critical if devices need to run on batteries or small solar panels for months or years. Longer range is needed to cover farms or remote monitoring sites without needing thousands of base stations. And resilience is key to cope with harsh weather or lack of maintenance.
Okay, before we get into the tech solutions, what are the economic stakes, especially when we look at the agricultural sector, which dominates so many rural economies globally?
The stakes are enormous, and they tie directly into global food security and rural livelihoods. The global market specifically for IoT and agriculture, think smart farming, was valued near $30 billion in 2024. But analysts project it's going to roughly double within the next 5 years. That shows rapid adoption.
Doubling in 5 years.
And it's estimated that smart farming systems, leveraging IoT sensors and data analytics, now cover over 60% of large, modernized farms globally. It represents a massive shift away from traditional, often guesswork-based farming practices towards precise, data-driven agriculture.
Okay, so the need and the market are there. But deploying 5G towers or running fiber optic cable across vast, sparsely populated rural areas is often prohibitively expensive, isn't it? So what specific, affordable, and resilient connectivity solutions are actually being employed on the ground in these regions?
Right, you can't rely on fiber everywhere. So we rely on wireless architectures specifically optimized for low power consumption and long range. The leading technologies here are things like LPWAN, which stands for Low Power Wide Area Network, and specific protocols under that umbrella like LoRaWAN.
LPWAN and LoRaWAN, what are their advantages?
Their key advantages are incredibly low cost for the end devices, the sensors, very low power consumption allowing battery life measured in years, and surprisingly long range, often capable of connecting sensors up to 10 or even 15 kilometers away from a gateway depending on terrain. This is perfect for monitoring static or slow-moving assets spread across large areas, like soil moisture sensors in fields, water level monitors in tanks, or even simple GPS trackers on livestock.
10 to 15 kilometers from one gateway. That covers a decent area. But what about the truly remote off-grid regions? Places where even putting up a LoRaWAN gateway might be difficult, or where there's absolutely no terrestrial signal of any kind. Think remote ranches in Montana, monitoring stations in the Amazon, or villages in the Himalayas.
For those completely off-grid scenarios, we increasingly utilize satellite IoT. This involves using small, low-power devices that communicate directly with constellations of low Earth orbit (LE) satellites.
So the sensor talks straight to space.
Essentially, yes. It bypasses the need for any ground-based network infrastructure entirely. This ensures continuous monitoring and data collection capabilities anywhere on the planet, independent of local terrestrial coverage. The cost for satellite IoT connectivity has also been dropping significantly, making it viable for more applications.
And you mentioned power is a critical issue. How are these remote sensors typically powered?
Crucially, almost all these rural IoT systems, whether LPWAN or satellite, are designed to be or are deployed as solar-powered. Often they run on very small integrated solar panels charging a small battery pack. This ensures round-the-clock monitoring capabilities despite irregular or non-existent grid electricity supply. Self-sufficiency is key.
Okay, so we have the connectivity, LPWAN, satellite IoT, and the power source, solar. How does this actually translate into real-world impact? Let's take a specific example. How does this change things for a smallholder farmer, maybe in India or Kenya?
For farmers, it fundamentally revolutionizes their operations through precision agriculture. It moves them from farming, based on tradition or intuition, to farming based on precise data. Networks of inexpensive IoT sensors are deployed in their fields, measuring critical parameters in real time. Soil moisture at different depths, nutrient levels like nitrogen, phosphorus, potassium, soil pH, ambient temperature, humidity.
A constant stream of data from the field itself.
Exactly. This torrent of localized data is then often processed by cloud-based AI platforms, accessible perhaps via a simple smartphone app. The AI analyzes the data and provides the farmer with specific, actionable recommendations. Things like, apply X amount of water to this specific zone of your field, or fertilize this section with Y nutrient, but not that section. It enables variable rate irrigation and fertilization.
So applying inputs only where and when they are actually needed.
Precisely. And the benefits are dramatic, especially for resource-constrained smallholders. Numerous pilot programs and commercial deployments have demonstrated that these systems can boost crop yields significantly, often by 20–30% or more, while simultaneously, and very importantly for drought-prone regions, reducing water usage for irrigation by up to 40%. We're seeing successful examples of this across India and parts of sub-Saharan Africa.
That level of efficiency improvement, higher yields with less water and fertilizer, is absolutely critical for both basic food security and improving the farmer's profit margin. But you said IoT in rural areas goes beyond just agriculture, right? Extending into vital social services like healthcare.
Absolutely. The potential impact on healthcare access in remote areas is truly transformative. One of the biggest challenges is the lack of diagnostic facilities. Getting tests done often requires traveling long distances to a town with a clinic or lab, which is time-consuming and expensive.
So how does IoT help there?
We're seeing innovations like MobiLab Global, which originated in India. This is essentially a portable, AI-powered, IoT-enabled diagnostic toolkit. It's designed to be rugged, run on solar power, and usable by minimally trained local health workers.
What can it do?
It can perform a surprisingly wide range of complex blood and urine analyses right there on the spot in a village, setting tests for things like malaria, dengue, liver function, kidney function, blood sugar levels, pregnancy tests. It delivers results in minutes.
So it brings the lab to the village?
Exactly. It provides affordable, immediate diagnostic testing in communities that have zero access to traditional laboratory facilities. This kind of remote monitoring and instant diagnosis can drastically cut emergency response times. Studies suggest by up to 50% or more in some rural regions, because the health worker knows what the problem is immediately and can initiate the right treatment or referral pathway much faster.
50% faster emergency response. In areas where the nearest hospital might be hours away by poor roads, that is literally the difference between life and death in many cases.
It truly is. And this theme of using IoT for early warning and resilience extends beyond healthcare too. It contributes fundamentally to overall community resilience against environmental threats.
That's so.
Networks of low-cost environmental sensors monitoring river levels, rainfall intensity, ground moisture for landslide risk, even air quality for wildfire smoke connected via LPWAN or satellite links can provide highly localized, real-time early warnings for natural disasters like floods, wildfires, or droughts. We see examples of such systems being deployed in disaster-prone countries like the Philippines for typhoon warnings or Nepal for landslide monitoring. This allows for faster community mobilization, targeted evacuations, and more effective preemptive resource allocation by local authorities.
That's proactive safety. Now, I found the concept mentioned in the outline about IoT enabling economic empowerment particularly fascinating. How can this technology help create new business models or ensure fairer profits in remote areas beyond just improving farming?
This is a really interesting area, moving beyond just monitoring into enabling new forms of sustainable local enterprise. One concept gaining traction is the IoT-enabled microfactory.
Huh.
Imagine small-scale modular manufacturing units set up in rural communities, perhaps running entirely on local solar mini-grids. They might be doing anything from processing local agricultural produce to assembling simple electronics or 3D printing spare parts.
Okay, small local factories. How does IoT fit in?
IoT sensors monitor the entire process energy consumption from the solar grid, Raw material inputs, production volume from the machines, quality control checks, all this data is logged automatically, and here's where blockchain can be integrated. The production data, energy usage, even sales transactions can be recorded transparently and immutably on a blockchain ledger
Well, I'll use blockchain for that.
to ensure fair and transparent distribution of profits. In cooperative models, for example, the blockchain record provides an undeniable, auditable trail of who contributed what, for example, raw materials, labor hours tracked via IoT, and how much revenue was generated. Profits can then be distributed automatically and equitably based on those verified contributions. We're seeing pilot projects exploring these models in places like Rwanda and Indonesia, aiming to foster genuine, decentralized economic ownership and create transparent, traceable supply chains originating right from the rural source.
That's a powerful combination. Local production, renewable energy, IoT monitoring, and blockchain for trust and equity. It paints a very different picture of rural development.
It does. The overall trajectory here is clear. By maybe 2030 or so, the synergy between increasingly sophisticated IoT, AI analytics, and eventually the widespread reach of 6G, especially via satellite, aims to move the needle significantly. We're moving from just talking about smart farms to enabling genuinely smart villages or smart rural regions.
So, creating autonomous, data-driven rural ecosystems that prioritize not just efficiency, but also resilience, healthcare access, and local economic empowerment.
Exactly. The hope is that technology becomes a great equalizer, enabling data-driven prosperity and better quality of life in rural areas without forcing urbanization, without compromising sustainability, and hopefully without widening the digital gap even further. But, and this is a crucial but, all this unprecedented hyper-connected infrastructure we've described across airports, cities, and rural areas, this vision of a cognitive planet, it comes with a very real, very significant set of risks, massive financial hurdles, and profound ethical questions that absolutely must be addressed proactively, not as an afterthought.
Yes, that feels like the absolutely essential pivot point in this discussion. We've painted this picture of an incredibly powerful, intelligent, interconnected system, but we have to interrogate the costs, the risks, the trade-offs. Let's start with the most immediate, practical hurdle, the sheer expense required to build this future.
The cost barrier is, frankly, immense. We're talking about staggering upfront capital investments, followed by significant ongoing operational costs for maintenance, upgrades, and energy. Just setting up the foundational private 5G and mobile edge computing infrastructure we discussed earlier, that alone can easily exceed $100 million for a single large international airport. And that's before you even factor in integrating large fleets of autonomous vehicles, deploying sophisticated AI software platforms, and retraining staff.
$100 million just for the network plumbing at one airport.
Roughly, yes, for a major hub. Now scale that up to deploying a citywide 6G network. You need an incredibly dense mesh of new base stations operating at terahertz frequencies, countless reconfigurable intelligent surfaces installed in buildings, potentially new fiber rollouts to support the backhaul, maybe even quantum communication routers for critical infrastructure. The estimated cost for a comprehensive 6G deployment in a large metropolis could easily exceed $500 million, perhaps significantly more depending on the city's size and density.
$500 million or more per city. That kind of funding requires completely new financial models, doesn't it? No single municipality or airport authority can likely shoulder that kind of investment alone.
Absolutely not. It demands fundamentally new, innovative financing approaches. We're likely to see a heavy reliance on long-term public-private partnerships, PPPs. In these models, private sector companies, network operators, tech giants, systems integrators would fund and build the infrastructure in exchange for some form of guaranteed revenue stream, perhaps a share of the long-term operational efficiencies generated, or rights to offer premium services over the network. Furthermore, city planners and infrastructure managers need to budget realistically, not just for the initial build-out, but for the high lifecycle costs. This includes continuous hardware upgrades, 6G won't be the last G, software maintenance, cybersecurity, and crucially, the significant energy consumption of these dense, high-performance networks.
Okay, cost is a massive hurdle. Now let's pivot to the security risks. When you connect literally billions of new devices, everything from smart lampposts and soil sensors to aircraft navigation systems and hospital equipment, you are exponentially increasing the potential attack surface, aren't you?
That is the core security nightmare. The hyperconnectivity, while enabling all these benefits, dramatically, terrifyingly increases the attack surface. We're creating a deeply interconnected system where a vulnerability or compromise in one seemingly innocuous component, maybe a misconfigured sensor, a hacked smart traffic light, could potentially ripple through and disrupt entire critical infrastructure systems, energy grids, water supplies, transportation networks.
And the attackers are getting smarter too, likely using AI themselves.
Precisely. We are moving rapidly into an era where AI must defend against highly sophisticated AI-enabled cyber attacks. Attacks that can learn, adapt, and find novel vulnerabilities much faster than traditional methods.
So how on earth do you defend something that is simultaneously so vast, so complex, so interconnected, and constantly in flux?
It necessitates a radical shift in security thinking and architecture. The old model of building a strong perimeter firewall and trusting everything inside doesn't work anymore. We need to move towards zero-trust architectures.
Zero trust. What does that mean practically?
It fundamentally assumes that no device, no user, and no network connection is implicitly trustworthy, regardless of whether it's inside or outside the traditional network perimeter. Every single connection attempt, every data access request, every transaction must be continuously verified and authenticated based on multiple factors: user identity, device health, location, the specific resource being accessed. This relies heavily on techniques like microsegmentation, breaking the network into tiny isolated zones so that if one part is compromised, the breach is contained. It requires continuous monitoring, strong multi-factor authentication everywhere, and AI-powered threat detection systems that can spot anomalous behavior patterns indicative of an attack in progress.
It sounds incredibly complex to implement and manage.
It is, but it's seen as essential for securing these hyper-connected systems. And alongside zero-trust principles, we also need to look ahead and address the looming threat posed by quantum computing to our current encryption methods.
Right, you mentioned quantum computers breaking today's encryption.
Yes, while large-scale fault-tolerant quantum computers are still some years away, the threat is considered serious enough that any large-scale deployment of long lifecycle infrastructure like 6G needs to plan for it now. This means starting the transition towards quantum-safe encryption, also known as post-quantum cryptography, PQC.
These are new encryption algorithms designed to resist attacks from both classical and quantum computers.
Exactly. Standardizing and deploying these new PQC algorithms across the entire 6G ecosystem, from the core network to the end devices, is a critical, urgent task to protect sensitive data flows, like financial transactions, government communications, critical infrastructure commands, against future quantum attacks that could otherwise render them insecure overnight.
Okay, huge technical challenges on cost and security. Beyond the technical defenses, though, the regulatory environment seems to be desperately struggling to keep pace with the sheer speed of this technological deployment.
That's putting it mildly. Regulatory alignment is severely lagging behind the technology curve across multiple domains. Think about it. Aviation authorities like the FAA or EASA need new frameworks for certifying autonomous aircraft and managing UAM traffic. Municipal city planners need new regulations for data privacy, algorithmic transparency in city services, and managing fleets of autonomous vehicles on public streets. Agricultural standards bodies need protocols for data sharing from smart farms. And internationally, getting consensus on crucial issues like spectrum allocation, particularly for those new terahertz bands needed for 6G, is incredibly complex and politically charged. We need updated, globally harmonized frameworks, and we need them quickly.
And within those frameworks, our sources consistently highlighted the deep ethical tension, particularly in smart cities, between the goals of enhanced safety and efficiency through monitoring and the fundamental right to privacy.
That tension is absolutely critical, and perhaps the hardest one to resolve. On one hand, yes, AI-powered video analytics monitoring public spaces can enable that 80% faster emergency response, potentially saving lives. Smart sensors can optimize traffic flow and reduce pollution. But on the other hand, the same pervasive surveillance technology, collecting data on citizens' movements, habits, and associations, 247, creates profound risks for individual privacy, freedom of expression, and could enable chilling levels of social control if misused. Finding the right balance is incredibly difficult.
How can we find that balance? What kind of governance is needed?
It requires robust data privacy regulations like GDPR, but potentially going further. Crucially, it requires transparency and public oversight regarding how AI algorithms are being used by city authorities. What data are they trained on? Are they biased? Who audits them? Furthermore, we must address the fundamental risk of bias and inequity being accidentally or intentionally embedded within the AI training data itself.
You mean if the historical data used to train an AI for, say, predictive policing reflects historical biases and arrest patterns?
Then the AI will simply learn and likely amplify those same biases, potentially leading to discriminatory outcomes in how city resources or security presence are allocated in real time. Smart systems could inadvertently perpetuate or even worsen existing social inequalities if not designed and governed very carefully.
So how do we combat that? How do we ensure fairer, more equitable AI governance in these systems?
This is where some really innovative, perhaps radical governance models are being proposed. One idea gaining traction, particularly in the blockchain community, is using decentralized autonomous organizations, or DAOs, for managing certain aspects of smart city data or algorithms.
DAOs using blockchain for city governance, that sounds like a profound leap. How would a DAO structure actually function in a smart city context?
Well, the core idea is to move away from a single centralized entity like the city council or a private corporation managing the smart city platform controlling all the data and decision-making. Instead, a DAO could use blockchain-based voting mechanisms and smart contracts to distribute governance power. For example, citizens or designated stakeholder groups could potentially vote directly on things like proposed updates to the traffic management algorithm, changes to the city's data privacy policy, or rules governing how anonymized public data can be used by researchers or third parties. The goal is to build in transparency, accountability, and collective decision-making directly into the operating system of the smart city, ensuring the technology serves the collective good rather than just top-down directives or corporate interests. It's experimental, but very interesting.
Very interesting indeed. A potential mechanism for democratic oversight built into the tech itself. Finally, one last major challenge. All this incredibly sophisticated, increasingly autonomous, self-managing infrastructure. It still requires highly specialized human expertise to design, build, operate, maintain, and govern it.
Yes, the skills gap is accelerating wildly. We are seeing a massive and rapidly growing demand for talent in fields that were previously niche, now becoming mainstream requirements across sectors. Think about traditionally non-tech sectors like aviation HR, needing to understand AI ethics, municipal service departments needing data scientists to interpret smart city analytics, agricultural consultants needing expertise in IoT sensor networks and precision farming software. The demand for data scientists, AI engineers, especially those specializing in complex areas like DRL and EFL, cybersecurity experts, particularly with quantum-safe crypto knowledge, and network architects who understand SAGIN and RIS is exploding.
So cities, airports, agricultural organizations, they all need to invest heavily in technical education and reskilling programs, both for new talent and their existing workforce.
Absolutely. It requires a concerted effort from educational institutions, governments, and corporations to build the pipeline of talent needed to actually manage this new cognitive infrastructure effectively, safely, and ethically. We're building the technological brain, as you said earlier, but we desperately need the skilled neurosurgeons, neurologists, and ethicists to operate and guide it responsibly.
A critical point. We're building incredibly powerful tools, but ensuring we have the wisdom and the workforce to wield them correctly is paramount. #outro.
So we've traced this really monumental journey today, haven't we? Starting from the immediate reality of AI-powered 5G airports that are already starting to self-manage and optimize their complex operations.
Right, moving through the vision of hyper-connected, potentially self-aware 6G smart cities, managing resources and mobility at an unprecedented scale.
And finally, looking at the truly life-changing impact that resilient, cleverly designed IoT networks can have in bridging the digital divide and connecting remote rural areas, improving agriculture, healthcare, and economic opportunity.
It's clear this convergence AI, IoT, 5G, 6G isn't just about incrementally faster networks or marginal efficiency gains here and there. It really is about creating a unified cognitive layer of infrastructure, a true digital nervous system for the planet, potentially linking every point, every movement, maybe even every decision in a web of data and intelligence.
Yeah, and if 5G perhaps made our urban infrastructure smart, capable of reacting and optimizing based on data, then 6G is explicitly being designed to make it self-aware, or at least much more autonomous and truly self-optimizing. The goal is for these complex systems, these hubs, to think, learn, and evolve in real time. But as we've stressed, as we build this almost unimaginably vast intelligence, we absolutely must maintain constant vigilance over its purpose, its control, and its potential consequences.
Which really leaves us with the final overarching question, a provocative thought perhaps for you, our listener, to consider as you move through your own increasingly connected, increasingly cognitive world. We are undeniably building the digital nervous system of the planet. Given the massive costs involved, the profound security risks, and the very real dangers of embedded bias and centralized control, Mm. What concrete ethical principles, what robust governance frameworks must we demand today to ensure that this vast emerging intelligence truly serves the entirety of humanity, not just a select few?
It makes you think back to that conclusion from the UN Digital Futures Report, which I think encapsulates the challenge perfectly. The smartest city is not the one that thinks fastest, but the one that thinks for everyone. Ensuring that thinking for everyone remains the core design principle is perhaps the greatest challenge of all.